My name is Marius Bogoevici. I am leading the ecosystem function inside the Phil City organization at Red Hat. I'm a long-term open source contributor, and I've worked a lot in financial services. For the past few years, I've been leading this engagement around the platform that we're going to talk about today. First inside OS Climate, and then inside FINOS. Together with me is my colleague Jey Paulraj, and I'm going to let him introduce himself.
Hi, my name is Jey Paulraj. I'm a chief architect, part of City organization Red Hat. My primary role is focus on building a data platform for a modern data science.
Awesome. So first, how is everyone today? How do you enjoy the conference so far? That's the best thing. All right, so let's talk a little bit of history and how we got here today. The origins of the talk today is in a work stream of the Linux Foundation called OS Climate, and the primary goal of the platform that we're building has been to aggregate and enable researchers, not climate researchers, but financial institutions to incorporate climate data in the way they assess risk. And for that, we kind of thought about building a data platform that's able to aggregate data from different sources and put it together. As it turns out, there's nothing inherently climate-focused in that. And all the goals that the platform has had ever since the beginning are congruent with many other types of financial, of financial services concerns, such as regulatory reporting, general data governance. And that's kind of that's how we got in here today, talking more about the use of this platform in a more general sense. And what we're going to do today is kind of walk you through the general principles, and we're going to see a demo at how it works in practice.
Okay, so I'm going to talk about the data mesh architecture, which is a modern data science data platform. The data mesh architecture is based on 4 key principles. Domain ownership. Domain ownership means the domain owner who owns the data, who creates the data, they manage the platform. If you look at legacy data platform, and the central team manages the data, they don't own the data. That's the gap between centralization and decentralization. So the key principle of the domain ownership means the domain owner who creates the data, they manage the platform. The second principle, data as a product. What that means, define the data as an API. Treat the data as a code. Instead of data as a data, you define the data as an API. Define a data as a code and expose an API. Same principle how you apply for the microservice, right? You expose your business logic as a microservice, that way any consumer can consume based on the content. The same principle applies to data product. Data product is not just a data. It contains data as well as a code related to the business logic and the metadata around the data. It's not just a data set. That way, anyone can easily discover the data, what it does it. That's the data as a product principle. The third principle is self-serve data platform. Instead of having a centralized data platform, it's very hard to manage if you go with the domain-specific data platform. So every domain wants their own data platform. They want their own data platform as architecture. The fourth principle, proprietary governance. This principle achieves industry standard policies and regulation for data interoperability. Since every data product owns a domain, you need to talk to different domains across the industry. How do I talk to different domains? That's the data interoperability, which achieves through enterprise standard and policy. These are the 4 principles behind the data mesh architecture. I'll show you the demo, governs all these 4 principles, how the data mesh architecture implemented in a cloud-native way. So these are the difference between data warehouse, data house, how data mesh architecture provide the better visibility and scalability on top of data lake and data warehouse. Single point of access for a data warehouse, ETL tool is required. For a data lake and data lakehouse, ELT. That's the latest trend. Instead of extract, transform, and load, database is extract, load, then apply the transformation on top of where the data is located. Database provide the query federation. That means you don't need to move the data between different sources. You can keep the data where it is originated. Using data federation, you can just combine all the data source and provide the data query, and based on certain policies applied for the standard. Separation of storage and compute. If we look at a legacy data warehouse, data platform, everything is as a one centralized monolithic data platform. For data meta architecture, it's decoupled compute and storage. That way, your data injection, data processing layers separate, runs on different platform, different infrastructure, and the storage runs on different infrastructure, so that you can independently scale your storage and your compute process. That's the key advantage of data mesh architecture. And no data movement. Since I said it's a data federation, you don't need to move the data. It's not optional. You don't need to move the data. You can combine all the data source and provide a virtual query federation. That's a data movement. And you can deploy it on any public or private cloud, and easy to access the data from anywhere in your platform. And last one is a unified way of accessing your data through SQL, regardless of where data is located. It could be a relational database, or it could be S3 bucket, or it could be any file system, but you use a standard SQL query to fetch the data, which avoids data movement.
So there's a lot of information there. Let's unpack that a little bit and look a little bit how we got here. First and foremost, how many of you are working day in, day out with data? Okay, call to show of hands. Working with data means different things to different people. So, data scientists are trying to understand the data. Data engineers want to shape and transform it in consistent ways. And of course, at the tail end of the process, you have application developers that want to build smart applications. And these are the three personas that we're building this platform around. All the principles that Jey was talking to you about are reflected in the interaction between these different personas. And one thing that we do not have is a problem of not enough data. That's going to sound controversial. There's a lot of data. What we don't really have is quality data. We don't have a good understanding of data. We do not have data that abides by specific standards. You don't have quality data. So in some sense, that's reflected. It's not just us saying that. You have many studies kind of showing that information, right? Like this is, for example, a study from Deloitte published in 2024, which basically said, look, 92% of the people think that the data that they need is not easily available to them, in a nutshell, right? The question, part of the problem is how we view data. And this is what Jey was talking about earlier, about the notion of a data product. The idea that, we're used to have data sets. And a long time, kind of data science has revolved around the idea, okay, someone's going to publish a data set, I'm going to find it, I'm going to find some raw data, I'm going to try to interpret it in a certain way. The notion of a data product elevates a little bit the concept of a data set, as Jey said earlier, with things like structure, with things like design, intentionality. I'm not just publishing and exporting some data from my systems. I'm actually creating something that someone will consume, and I have to think about who's going to be the beneficiary, who's accountable for producing this data set. We're in the open source world. One of the things that people have a hard time understanding with open source is that it's not just about having access to free software. It's having access to a community of maintainers. So in the same way with data products, it's critical to understand who maintains your data set. And of course, things like, discoverability and governance. And there is a big interest in building data sets. Like, again, other studies, this one by KPMG, shows that 92%, probably not the same 92%, but the same number of executives think that data products will be critical for the success of their organization. And yet, we do not necessarily see widespread adoption of data products as as an entity across the industry. And part of the reason why that is happening is because we need to apply the same principles that apply to code, we need to engineer these data products in many ways in the same way as we engineer our software. So what we're talking about today is really two concepts: data as code and a data platform on which data as code runs, everything backed by open source. These three components together offer you both a platform in which you can evolve quickly, have transparency, and also have standards and the levels of openness that you require to build data products, which is becoming much more important, in this, like especially when generative AI comes into play. So you bring in concepts like versioning, CI/CD, and we're going to see them in a moment. Collaborative review, and what Jey was talking earlier about self-servicing. We're going to see an example in which you can take an entity and a Git deployed unit and turn it into a deployed data product using the same principles that you use to build and run code. The complement to that is, yes, we have this idea that we can build data products as these kind of like version discoverable entities. Who's going to run them? What's going to happen to them? How do they become materialized? So this is where the data platform concept comes into play, complementing it. So having this self-service platform where I can bring my data, run it, deploy it, and kind of be able to look at it becomes critically important.
Yep. So the data platform consists of 3 layers. The data management orchestration layer, which is we are using Airflow as a data pipeline orchestrator, and lineage, data lineage, how data flow through your pipeline, starting from our origin to destination. It completely track of your data flow. That's our lineage. There's a more of a management layer, and the middle layer is more of a data injection and a data transformation. As I said before, the data mesh architecture decouples your compute from the storage. That way, can scale independently. For the data transformation and data injection, you can use choice of your tool, whatever the technology used in your enterprise. The Spark, Trino for a data injection. Mostly Trino used for data federation, because you don't want to have a data movement. We can keep the data where it is originated. Through Trino, you can connect all the data source and fetch over a single data view. You get a more of data virtualization. And Spark for any batch process, long-running batch process, you can use a Spark cluster to inject the data from different sources. So the middle layer is more of a data compute, more of data processing. We can independently scale your data processing engine. And the bottom layer is storage. Yes, storage decoupled from the compute. So we use Iceberg. Iceberg is one of the tabular format. You can store your data as a tabular format to avoid the detailed process. All the data directly can store in our file system, and it provides a metadata and a catalog. That way, if anyone want to discover where the data is stored, which packet is data stored, through metadata and catalog, you can easily view your data. That's Iceberg. Iceberg came from Netflix. Netflix used Iceberg as their data processing layer. In all the data stored in S3 combined storage. It could be Manivo or AWS S3, Google S3 storage, as long as any S3 combined storage. These are the 3 layers data mesh architecture implementation. And I'll show you the demo.
Yeah, so as we kind of build into the demo, here's what you're going to see, right? Like, who is familiar? Like, what does this look like? Pretty much, it's very similar to the inner loop development model for applications, right? You will be able to iterate locally on your data product definition, build the data pipelines. You're going to see them in a moment. Running with, you're going to build your DBT models. You're going to build transformations in Spark or in Python or everything. You're going to package them together, commit them, and then, as part of your deploy process, use a CI/CD pipeline. In our case, we use Argo to trigger the orchestration of the transformations, to automatically register the metadata. We actually use their open metadata, but in fact, we're using Marquez in our process. So, and then register the lineage for the application. This is very, very important because as a consumer of a data product, I don't want to have just the data. I don't want to see what the transformations were. I want to understand where this data comes from. I'm going to see an example in a moment. So just by taking that code from Git and deploying it, this kind of the deployment happens automatically. And at the end of the process, and you're going to see this again, we consume this data. We use the data that we just published, for example, to up on data metadata, to discover data sets. We use the lineage information to inspect where this data is coming from. We use data sources like Trino, for example, to pull it into a Jupyter notebook and investigate it. So, Jay, you have the deck.
Yep. Let me see. How do you? Okay. So I deployed the whole data mesh implementation in Kubernetes platform. So this is an OpenShift. OpenShift is a Red Hat Kubernetes platform, but it can deploy to any Kubernetes platform, not really the Red Hat. So how do I build it? The whole data platform deployed through Arco CD. I did deploy it through my Helm chart. I have umbrella Helm chart. There are a lot of components in data mesh architecture, right? It's a compute layer, multiple components on the data processing engine, and the storage. Storage, I used MinIO as my storage. All data injection go through the data injection layer and persist in S3 packet. MinIO is the S3 combined storage. And through Iceberg, I persist all the data as a tabular format. And all the metadata schema are created in the Hive catalog, Hive metastore catalog. That way, Trino can retrieve the data from S3 storage using the Hive metadata. Okay, I'll show you all these components here. Let me. I walked through the whole the data as a product journey, starting from how the data scientists write their data product as a code and deploy it through agile methodology using a CI/CD pipeline. So I can have all my data product as a Python code in Airflow. They have a separate Git repository, and I can, once my code is ready, I can check in my code to Git repository. Once I come into the main branch, it's automatically kick in my CI/CD pipeline. It deploys my all data product to the Airflow runtime engine, where you can process the whole data processing. It's all one. It will deploy all the components within 5 to 10 minutes. So this is my Airflow. This is where all my data products going to run it. This is my storage. So MinIO. Any S3 combines, you can use AWS, any S3 combines storage. So we look at here, everything is empty. I don't have any my data pipeline. I'm going to deploy later on from CI/CD pipeline. Right? Trino is my query engine. Trino. So I built the Trino cluster. Trino is kind of more of a server-client architecture. You can have one master and multiple worker node because you have a high volume of data I want to fetch from the S3 packet. Trino is kind of a query processing engine. If you have a heavy, large volume of data, you need a big cluster because you share the query plan to a different node, it execute independently and get you the data very quickly. This is my Trino query engine. Okay, so how do I deploy my my data product, which is data is a product is nothing but a source code. All my data products are my GitHub. That's my source of truth. These are my DAG. These are my data pipeline. I define all my data source. Where is the source for my data? And extract the data from the source and apply the transformation rule, then deploy that into destination. It could be S3 packet, or it could be a relational database based on how you are transforming, how we are storing clean data and curated data into the backend storage system. These are my data pipeline. So right now, nothing in my MinIO. So when I check in my code from my source, it kick in my CI/CD pipeline, I move all the data source to deploy to the MinIO. Then my Airflow has a sync tool which sync all the data from MinIO to my Airflow runtime engine where your data pipeline get processed. Okay, so let me go and trigger my pipeline. So I create a Git action. Git action is a CI/CD pipeline. So I already deployed. I'm going to trigger that again. So I trigger my pipeline. It is automatic. Whenever I check in here called main branch, automatically kick in. Now I can go see my MinIO. You can see all my data comes here. Initially it was empty. Now we can see in a few seconds, you can see all the data under the data folder. See, it was initially empty. So all my data product, which is nothing but a code, it moved into MinIO. So now I have the sync tool, which is already part of Airflow. See, all moved to here. Whatever data in my GitHub is all moved into Airflow. So now I can kind of schedule the time. Each data pipeline can schedule it based on the scheduler, it processes it, or on-demand. You can go on trigger your pipeline anytime based on on-demand. So I have two the data pipeline. One is a credit card fraud detection. So this is like kind of multiple credit card transaction from different sources. This is kind of more of a graphical notation, right? So when I took it extracts the data from different data sources and do some transformation and push the data into the final storage S3 packet. So I'm going to trigger this one. You can visualize the whole process now started. Look at here, it's a two data source. And combine those two data sets into one data source. Then I push into the S3 packet. It'll take a little bit of time. And inject it into the final destination data source. So now I can use a Trino query engine to fetch the data from my S3 packet. All the data now stored in the S3 packet. Okay. So catalogs, so I have multiple catalogs. Iceberg, remember the way it pushes data into the tabular format in S3 packet is Iceberg as one of the catalog. It's not necessarily S3 packet, you can also store the data into a relational database. As I said before, Trino is a query engine, it's a federated query engine regardless of where data is stored, you can combine all the data sources, you can view the data using the standard unified SQL language. So I'm going to see all the tables in my Postgres. Because my data is stored in so public database, so I can show tables. So these are the tables. These are 3 tables just now I processed through my data pipeline, like a credit card transaction from different sources and combined in a neat table. This just now I showed the pipeline. This is the pipeline. This pipeline persisted data through Trino and stored in the S3 packet. So I can use same SQL to see the data from Trino by engine, query engine. So I can say select one of the table. I can take these, the final destination table. So these are tables stored in S3 packet. The Postgres database. I'm querying through Trino query engine. Okay. So now the same data I can use as a data scientist. I can use Jupyter Notebook to model my train my model using this data. So I built a simple notebook, Jupyter Notebook, to train the model that fetch the data from Trino. That's now I query from the CLI command, right? So now this is an API connect to Trino. Trino is hosted on the Open Kubernetes, and this is my catalog. Postgres is my catalog, and this is a public schema, right? So I'm going to fetch all the data from Trino. As a data scientist, so I wrote my model. This is my features. I'm extracting the feature from my data, and what is my flag. So that based on this model, I'm going to identify whether it's a fraud detection, fraud transaction, and non-fraud transaction. So this is a key features. This is identified. My model get trained. So now we can see that there are 2 high-risk transactions. From my data, there are 2 transactions is a fraud transaction. As a data scientist, I can have the whole data journey from collecting the data from the source and do the transformation and persist the data into S3 combined storage. Then as a data scientist, I can go to my Jupyter Notebook, I can train the model on time. It's just one platform. As a domain owner, I manage my own platform and deploy my data product as a code. And that way it follows the agile methodology, follow the same software engineering principle. Okay? And also I can anytime, let me show you other, how do you access the data through, as a data analytics, I want to see the same data from analytical tools. So I deployed Superset. Superset is one of the dashboard. So from here, I can connect my Trino to fetch the data from storage, S3 combined storage, or from database, wherever. I can use Trino as a query federation query engine. It connects to all the data sources. I can visualize my data. So let me connect Trino through superset. I already have all the connection, the configuration. So this is my Trino connection. I can show you how it is connected. Look at here, Trino at Iceberg is 8080, the port. Right? So now I can go and visualize all my data through the dashboard. Import the dashboard. I already have that dashboard for my data. Oh, I don't have that. Let me run the data. Go to Airflow. This is another demo, single mortgage. This is a mortgage application for disaster recovery. All the like Fannie Mae, Freddie Mae, they collect the data from disaster recovery from particular region, and that data get exported through the my data product data pipeline. So load the data from the Excel sheet and process it and pass the data into the Minaway packet. It's running it. Yeah. Oh, okay. It takes a bit of time. It's processing a lot of data from the Excel sheet from the Freddie Mae, and process the data into, transform the data and put it in the S3 packet. Yep, it's almost done. Now I can go and visualize the data into superset. Yep, just now I process, I can see the whole data from here. Yep, that much covers the whole.
It would be interesting, like if we can show the lineage data in Marquez.
Yeah, so you can also see the lineage, data lineage, how your data pipeline process from your source to destination during the transformation, what are the data get modified, which transformation get modified. You can clearly see more of discoverability and observability, how your data get fetched from source to destination. That's a different tool, Marcus. Marcus is a data lineage tool. So whatever the data pipeline you're processing through Airflow, it collects all the events, all the data extraction, transformation, any modification, the whole observability collected from the Marcus lineage tool. So you can see if anything failed, it tells you exactly where it is failed, why it is failed. It's more kind of reliability. You can go back to, if you make any changes on your data set, you will make changes on any of your schema, you can easily verify what should be the impact on your data pipeline. Okay, so let me show you that data lineage, how it is formed. So these are just now ran all this data set. Sorry, data set. So Postgres, okay, see. That's the one, credit card transaction. So I have two data source, data source 1, data source 2, and what are the data sets, what are the schema. There are multiple data set schema, and it's a final destination schema. So let's say if I change any of my schema, you can come back out to the data lineage, see where's the impacts, how your data get modified, which data transformation modify your data. It provides a complete observability of your data transaction.
Thank you. Thank you, Jay. Can you put that down for a second? So we're at the end of it, and definitely don't want to sit between you and between us and the final reception. Just wanted to wrap things up a little bit on kind of what you saw and the general idea. You've seen us putting together a number of tools that are very good at what they do. Airflow, fantastic for writing DAGs for data transformation. dbt, fantastic for writing transformations. Marquez, fantastic for building data lineage and integrating with other tools. CI/CD, for example, Argo, fantastic at taking something and deploying it on a platform. Everything running on top of Kubernetes, which is great at running distributed systems. We took it and put it together in order to build that notion of a cohesive data platform that applies the principles of data as code, as you've seen before. The code in the repository kind of coming to life by being deployed through Argo, and then finally, being able to be either queried in the Jupyter notebook, or you could write an application, right, and so on. What's our ask, right? What's your takeaway? This is an open source project. This is an open source community. The ask is, if you work with data, be part of the community. Come and use the platform to consume data. Create new data products. Use the platform to create new give it a try. If you're more infrastructure inclined, come work with us to work together to solve these data governance problems in financial institutions by expanding the platform. So all in all, first we wanted to kind of share with you what we did, but also we want to invite you to participate as part of the community. Feel free to reach to us. We have our emails, you have the contact information for the data commons. Like, this project still lives under the data commons in OS Climate, but eventually it will move up to FINOS and be part of it. We're at the end. We're still here for questions. So if you have any questions, we're happy to take them. If not, you can find us anywhere around the conference.
Yeah, the components what we deployed in the data platform is 100% open source. None of them is proprietary. All of them is open source. Like Iceberg, it came from Netflix. Trino came from Meta, Facebook, and Airflow, Airbnb. So all from different proven technologies, not just like somebody put in the community right now. It's all proven. It's all in production from big enterprise.
I'll open up there.
So you can go and build your own upstream community, or if you want enterprise supported, each component has their own certified supported vendor, like a Trino from Starburst. Starburst supports the Trino if you want to go with the supported version. Same thing, Iceberg. Iceberg is part of the now Databricks. Iceberg Databricks has the same specification, like a data lake. Delta Lake is the same as Iceberg, but Iceberg is the new standard. It's better than Data Lake, so that's why Databricks uses Iceberg. If you want to go with the supported version, you can go with the Databricks. But if you want to build it yourself, it's all upstream proven technology.
We're on time, so maybe one question. Sure.
Yeah, great presentation. Definitely learned a lot. I just had one question. I was wondering if there's any examples you guys know of organizations using data mesh to create pipelines for training LLMs.
The question was, any examples of organizations using data mesh for training LLMs? I don't have, some of that information is proprietary. So, I would say right now for LLM training, particularly because the LLM training is specifically done on unstructured data, in particular, there is a need, like the data mesh concept applies pretty well there, but I haven't seen mostly applied for structured data, for creating, especially things that feed the, more along the lines of, of a RAG, fine-tuning or like a fine-tuning pipeline or something like that. So in general, they're,
I'm working on a project is part of the Linux Foundation, Edge AI Ops. Edge AI Ops, like nowadays a lot of edge computing, right? A lot of solar, like if you have a solar energy, the plants on different location, how do you automate the whole operation of the solar panel or a remote edge operation? So we collect the data from different edge location and store the data in a centralized location and use LLM to generate the content based, okay, this device generating this much of data and generate the report using LLM. So it's part of the Linux Foundation project. If you want, I can send you the link. You can contribute.
Thank you.
Thanks, everyone. And
Thank you.
yeah, let's stay in touch.